Hi everyone, you're welcome once again to MOG Economics YouTube channel. In this class, we are this class basically is going to be a continuation of what we started in the last class, and that was um, the Taylor series, the Taylor function. So today, you will recall from the last class or the last two classes where we taught the concept of Taylor series. We introduced this formula, which is the Taylor series expansion with the remainder term. Now, looking at this, we have this, which is the expansion of an arbitrary function, but here with a remainder term, which is denoted with the r subscript n. So now this can be written as this. This one stands for this, and then the remainder term. All right, but now there's an issue here because here we solved the question that was when we introduced this formula, and when we only rewrote this, we couldn't have like a specific form for this particular entity here. So but in this class we need to know the exact form of the remainder term. And now there is a concept called the Lagrange form of the remainder, which helps us to specify the exact form of the remainder term. So here the exact form, following the Lagrange form of the remainder, the exact form is this. That is r subscript n. This is the function we are dealing with, raised to the power of n plus 1. Then this measures the deviation. This is what we wish to expand our function around, and this is what we eventually expand it around. So this, the difference between these two is just the deviation. Then this measures the specific value between these two values. Okay, so now if we assume that the n is 0, that is, in this case, we are dealing with the original function. We are saying, okay, we are the first, the zeroth order of our differentiation. This is n equals 0. If we substitute this here into this formula that we have here, this Taylor formula, this is going to be reduced to this. So that means within this bracket here, we're only going to be dealing with this. Then every other series of derivatives will drop out of the function here. And then because we already specified the term for this, we already specified the form rather for this, if we substitute the value of 0 here into this, it will be reduced to this. 0 here, 0 plus this is 1, which is the first order derivative of this. And then substituting 0 here, you have 1, and here again also you have 1. So here, so from here, bringing this to the left hand side, we have this minus this equals to this. And now this actually represents a theorem, a specific theorem in mathematics, which is the mean value theorem. And what do we mean by the mean value theorem? The mean value theorem here measures the difference between this, the product of the difference between this and the derivative of a particular value evaluated at that point. Or let me say it exactly the way it is written here. It is the product of the difference and the derivative value evaluated at this point. This is the chosen value here. That is the value in between these two. So it is the product of the difference and the evaluated value in between this. So now, what's the point of trying to uh, build up this, taking this formula of Taylor series formula further? Now, the basic reason is we want to see the usefulness in the development of the general test for relative extremum. Yeah, and that's basically why we are taking this further. So now, before we proceed, at this point, I would like us to understand what we mean by the concept of relative extremum. Now, from our introductory economics class, mathematical economics, we were taught that in testing for the relative extremum of a function, it has to pass through two basic tests. First one is the first order test, at the point where you establish the stationarity of the function, and then once it passes that test, you have a specific value which is evaluated at the point where the function is zero. Then you move to the second order, the differentiation, where you differentiate again and see, you now evaluate the function at that particular point. So if it is negative or positive, you then decide whether it's a relative minimum or maximum. So basically, a function is therefore said to be at a relative maximum or minimum when it is evaluated at a specific value if the difference, which is this and this, and you pick a 2 points and then you take the difference is either positive or negative for values of s in the neighborhood of this, both to the right and to the left. Both to the right and to the left. So now to make it a little bit more clearer, we can denote or represent that graphically. Now, looking at the first graph here on the left, here we have a function. In this case, this curve here is bowed inward, and it shows concavity. So here we identify 3 points on this curve. This at the middle is x naught, which is the point in which our function is specifically expanded around. Here we have two different points, one to the left, picking a point to the left, and then another one to the right. So basically what we're trying to show is, okay, either moving to the left or right, we are going to see that, okay, the value will still be negative, showing, okay, we are dealing with a maximum function and the result of our second order differentiation is going to be negative. Now looking at this, if you move to the left, that is here, if the chosen value, our s value is x1, and then here we have s naught, we take the difference, notice that this is less than 0, meaning it is negative, the difference moving to the left. And at the same time, if we pick a neighbor, okay, now the reason this is less than 0 is this. Looking at this curve, you notice that the point 0 that we identified here is bigger than these two other points here. This point here is bigger than these two other identified points. Now what that means basically is, moving to the left, you notice this is higher than this, so meaning the function evaluated at this point is bigger than this, which is this greater than this will mean negative. And if we look at this to the right as well, here this is still bigger than this. So if we take the difference again, we say this minus this will be bigger than this, and the result will be negative. Being less than 0 means it is negative. All right, now looking at the one on the right, this is bowed outward, and we also, again, we are identifying 3 points on the curve, is x naught, and then we have chosen two values, neighborhood values now, this and this. So again, if we take the difference here, we evaluate the function at any point around this specific value to the left and to the right, we notice that, okay, in the case of, okay, let's start from the left. Here we have, so in this case, we notice that the result of the difference is positive, because here this value here is less than this is less than this, so this is bigger than this, so definitely the result will be positive, and that's why here it is greater than 0. And also, when we look at this to the right, when we choose a specific value to the right of this and then take the difference again, we have something like, again, it is positive because Here again, this is less than this, and this is bigger than this. Here the value of the function evaluated at this point is bigger than this, so this is positive. So then what we then say now is moving to the left or to the right of this particular function here gives a minimum, while here this is a maximum. When the second order, we recall again that when the value for our second order differentiation is negative, we're dealing with a maximum function. It is concave and maximum, and the one for minimum we have convex, and if the sign is positive, it is a minimum. All right, so now going further, at this point we are going to be all right. So at this point, um we are gotten to the point where we are going to use the Taylor's um, formulas to develop the general test for the relative extremum. So now we are assuming that we are dealing with a continuous and finite arbitrary function. Now, I believe if you recall from your elementary introductory mathematical economics, we were told that for a function to be differentiable, it has to be continuous, and that's the first condition. It has to be continuous, and it just should be differentiable at every point, particular curve. So those two conditions have to be present for you to say if a particular or a given function is differentiable. Do you understand? Now, here, assuming a continuous and finite arbitrary function, this is the function here. Taylor series can be used to expand. Now, this is just what we have. This is still the Taylor series formula with remainder, one we developed just not quite long. So now here we have just rewritten it. So instead of having the phi sign, and then so this is written in form of the Maclaurin. It's written in the Maclaurin form. We're having f of x and f of, so you see the notations. So instead of using the phi sign, we are using the f of in this case. So still the same formula, and here you notice that we have n plus 1 terms in the sum series. Now in this series we have n plus 1 terms, and what do you mean by the n plus 1 terms? Now the n plus 1 terms here is talking about, now the definition of the n plus 1 terms in this case is quite different from the one we have been used to. Now the n plus 1 term here is only saying, okay, here we have the total number of series in this expansion is n, plus this one here stands for the remainder term, this last term here, which is the remainder term. Now we already developed the form. We already know the form of our remainder term. So this is the remainder term, and then this is it. So this shows that, okay, we have this here is just our original polynomial expansion, the original function of which to expand around, and then plus the remainder. So now this here is the total number of entities within this is what we have as n, and then here is just the remainder term, and this stands for the remainder term in this case. So now the goal therefore is to be able to choose the right n value, so that we know, okay, to what order we have to have our Taylor series, to know, okay, if a particular function is going to be a minimum or is going to be a maximum. So the most important thing at this point therefore is being able to choose the right n value, which it simplifies our task, and we can easily know if the particular function we are dealing with is an extremum, whether it's a minimum or max. So at this point we are going to be looking at 4 cases on how we can choose the right n value. So we have 4 cases here. Now the first case rather, here is an assumption that the first derivative value is not equal to 0. So what do you mean by the first the derivative value is not equal to 0? Here, going back to our original function, their original formula, from here, this is not zero, but others are assumed to drop out of the function. It means we are going to have our Taylor's formula up to the point where this is not equal to zero. So this is what I mean. Going back to this function here, we are now again at this point we are assuming that n is zero, and then so if you say n is zero, it means on the right hand side, here, which is on this side, we are going to have just a single term. So here, this is what we have. Looking at this function here, we have just this term here, which represents the remainder term in this case. So this is the remainder term. So that's just a single term. Like I said the definition of this n plus 1 term is talking about this, in this case, the total number of elements within this, and then the 1 here stands for the remainder term. So here, assuming n is 0, it means we have just the remainder term. If we evaluate this 0 plus 1, that's 1. That means we'll only be having just a single term outside after rearranging. Because here, when you put 0 as our values, when you place 0, then here you have just only this. So if you take this to the other side, okay, this is already the function. So it means you are just having the first order. This one is just what you have here. So now we are assuming that this here, now to determine the sign, the question now is to determine the sign of this function. Now here we are assuming this is continuous, this particular derivative, this is continuous. That is, it assumes the same form as this. It is this and this is continuous, so it has the same value as this. So because it's continuous, it has the same value as this. But now for this one, the difference here, to decide whether this is a minimum or maximum. Now, from our graphical illustration in the last class, if this value chosen either to the left or to the right is lesser than this value, that means it's a maximum and it is negative. So if this is negative, and now knowing that, okay, this particular one follows the same as this, so in this case, the only issue that we are faced with is knowing the value of this one. If this is negative or positive, then we can be sure that the overall result will either be positive or negative depending on this. So we are sure of what this will be. That is, if in this case the value chosen around this is lesser than this, it's going to be negative. And the question to now ask is, what value will this assume? So once we know the value of this, and then this is decided, we can say whether it's a minimum or it's a maximum. So here I said, once we decide whether this is either negative or positive, and then this, because now looking at this, in this case, I said this particular derivative, this one, depends on this. Now we assume it is continuous and differentiable. We assume the same form as this. But now in this case, we are assuming that this first order derivative is not zero. So because it's not zero, it we are not really very sure if it's positive, is going to be positive or negative. But once we are able to decide, okay, whether it's positive or, then we know the result, the final result here. Now for the second case, we are assuming that the first order differentiation is zero. Okay, all right, do not really bother if this looks complicated, because at the end of, after we have presented all the cases, we are going to take 1 or 2 examples just to clarify it further. So now the second case here, which is case 2, is now we're assuming that the first order differentiation is 0, and then second order is not equal to 0. So now we are increasing the degree, which is the number of terms. Here we are increasing it to 1. in the first case it was 0, we assume it to be 0. So in this case we're increasing it to 1. Now when we're increasing to 1, that means the total number of terms on the right hand side of this our equation, on this our formula, will now be 2. That is, this, we're having this, and then the remainder term. If you substitute this value of 2 into this, we have here f prime prime, because n is 1 in this case. So you substitute it here, it's n prime prime. Then here, this is where I missed that. Yeah. So this is supposed to be square. So you substitute the value of 1 for n here, this will be square as well. So, and that's that. Now, again, we are assuming that okay, this is also continuous. This is we have already established, in fact, from here we have established that okay, this is continuous, because but in this case our first order differentiation is 0. So this is assumed to be 0 at this point. So here this reduces, this is 0, so this drops out of the equation, this drops out, and then we are left with just this. So this is therefore, now because this is assumed to be 0 now, this drops out from the assumption here, this drops out, and then here we are left with this. All right. So, and then which this can further be written as, okay, let's see if we can utilize this side. Can further be written as, this is can be expressed as 2 times 1. This is 2 factorial, so this is 1 over 2 this squared. So now again, this will depend on the sign of the values we have that's around this specific value. So if in the case of the graphical illustration that we considered the other time, if these values, the values are chosen around this is less, like if moving to the left or to the right, the difference here is negative, that will be a maximum. And if it is positive, moving either to the left or right, that will be a minimum. Now this, again, the value for this depends on this, the second order. Now again, this value here, in this case, depends on the second order derivative of this, of the actual function, which is in this case now, because here we are also assuming that this is not 0. So now if this is less than 0, that is negative, that will be a maximum. And if it is if this is greater than minus, that will be a minimum. So this, the result, the sign of this will now depend on whether this is greater than 0 or less than 0. All right. And now moving to the third case. Again, now you notice there's a pattern here. Okay, all right. At this point, we need to understand that okay, we do not, in all cases, we do not necessarily have to go through all these 4 cases. So there are situations or scenarios that will only warrant you to maybe stop at the second case or apply it up to the second case. So depending on whatever question you are asked or the problem you're asked to solve. So it doesn't necessarily have to go, you don't necessarily have to go through the 4 cases. All right. So now moving to the third case. Here again, like I said, there's a pattern. In the first case, we are assuming that the first order derivative is not zero. Now in the second case, we are assuming now that the first case is zero. Now the first order derivative is now zero, but moving to the second order derivative, it is unequal to zero, that is not equal to zero. So here the third one now is, we are assuming now that the first and second now are zero. Now we are assuming the differentiating the first time and second time, those two are zero, and now the third one is not equal to zero. So how, in that case, how do we determine our relative, our function, how do we know whether our function is a relative minimum or maximum? um for the second case, like I said, we have just two entities to the right of this particular formula. Now for the third case, we are having three entities, because now the total number of terms here from here has been increased to three. We are assuming that the first order derivative and the second order are both zero. So in that case, this and this will be out of the equation. So here this will be zero, and also this will be zero. And we are left with just this. So here 3 factorial can be expressed as 3 times 2 times 1, and that gives us 6. So here we have this. Now again, we are assuming that the third order derivative of this is continuous and it is the same as this. But because in this case, this is raised to the power of 3, this is the third order differential, it is an odd number, and in that case, it is not a square, unlike the second case where we could easily decide whether the sign will be positive or negative. But because this is an odd number, it's going to be negative. The sign is going to be negative. If you're having the sign 3 times, let's say we have, okay, this we can easily demonstrate this. Let's think of the number, let's say 1 in this case, and then we are multiplying that 3 times. Let's say we have negative 3 times. If we have negative 3 times, the resulting value will be negative. And if we have positive 3 times, it will be positive. So in this case, if this is negative, then here this will be negative, and if this is positive, this will be positive. So, and the value here, we can also determine this after choosing two given values around this particular specific value. So if moving either to the left or to the right, the result of this is negative or positive, we can decide if it's a minimum or maximum, just like we have done for the other previous cases. Okay, and now the final case is just the nth order case, where um, we have a specific nth value. Now in this is the third case. We are differentiating to the third, we are having the third derivative value, but in this case we have the nth derivative value. So that means the series in our formula continues like that up to the nth degree. So here again, it means now the assumption at this point will then be, okay, the derivatives before the final one, which is the nth derivative, which is not known now, except we know the actual value. Okay, so those other ones will be zero, and then all those derivative values will drop out of, and in this case I have not shown them, so just to save time, so they will all drop out of the equation, and then we will only be left with the remainder term, which in this case will just be the nth value, and then p and this, and then raised to the power of n. So again, this here varies if n is odd. That is, if we agree, well, understand what we mean by an odd number or an even number. So if this is an odd number, this power here is an odd number, this will change, the sign will change, will alternate. So in that case, it will be some sort of an inflection point, like where the curve will change from being a minimum to a maximum, or from a maximum to being a minimum. So the sign varies. That is now, but if it is even, if this sign is even, let's say 2, 4, 6, or something, or so on like that, this will remain unchanged. It will be positive. To remain unchanged. Now, and here, this also follows. Now, we are assuming again that this is continuous and differentiable. This will depend on this. So, if this is at maximum, definitely this will be at maximum. And if this is at minimum, that is, if this is less than or greater than 0, this will also be less than or greater than 0. That's it. So, we have come to the end of um, the application of Taylor's formula to determining whether a particular function is at minimum or maximum. So at this point, I don't know if you have any questions, to do well to drop them in this comment section. Very quickly, in the next class, I'm going to be looking at real examples, because in this case, these are just proofs. So in the next class, we're going to be looking at real examples that we can work with, so at least we understand all of this better. All right, see you in the next class.